Welcome to the deep dive. Great to have you with us again. This is episode 5 in our series looking at MySQL Group Replication and InnoDB Cluster. Today, we're going to step back a bit from all the cool high availability stuff in group replication. We're tackling something just as vital, maybe even more so, understanding its limitations and constraints. Think of this as the essential field guide, for actually using GR in the real world. We'll look at where it hits its limits, helping you kind of anticipate challenges, design better systems that are robust and, well, reliable. So for today's roadmap, we're going to unpack quite a bit. Things like GTID restrictions, challenges with certain isolation levels,
Yeah.
transaction size limits, even the max number of servers you can actually have in a group. It's pretty packed, but really useful stuff.
Absolutely. And understanding the limits is just as important as knowing the features. It's about setting realistic expectations, planning ahead. And before we properly dive in, we should mention that a lot of the insights we're discussing today were really well laid out on kedar.nitty-witty.com. It served as a great primary source for pulling this all together.
Right, good point. Okay, let's get into it. We know MySQL Group Replication, GR. It's built for high availability, right? For resilience. But to use it well, avoid those nasty surprises, we really need to get our heads around its specific limits. Know the boundaries.
Exactly. That's a perfect starting point. And what's really interesting, something highlighted in the material, is how some limitations,
Yes.
the ones we usually link with multi-primary mode,
Yeah.
they can actually pop up even when you're running single primary.
Oh, really? How does that happen?
Well, typically during failover events, you might be humming along fine in single primary, but a failover happens and suddenly you're facing issues that look a lot like multi-primary conflicts if you weren't prepared. It's a potential blind spot for sure.
Wow, okay. That is a blind spot. Definitely reinforces why we need to cover this. So let's dig into the specifics. Maybe start with something foundational. GTID restrictions. My understanding is GR relies heavily on GTIDs. What are the implications?
Yeah, you're spot on. GTID, the Global Transaction Identifier, it's really the core mechanism for MySQL's transaction-based replication. Every transaction gets a unique ID, system-wide. And because group replication builds its whole consistency model on top of this GTID replication, well, it just inherits all the existing limits and, let's say, quirks that come with standard GTID usage.
Okay, so it inherits the baggage, so to speak.
Pretty much. The key thing is you really need to look at how you're using GTIDs before you implement GR. If you've got workarounds or specific GTID setups already, expect those same challenges to carry over. It's like checking the foundations before you build the house. Saves hassle later.
Right, right. Solid advice. So if the foundation has limits, the building does too. Makes sense. Okay, moving on from that. What about something like upgrades? You'd think an upgrade always helps, but sounds like there's a catch.
There is, yeah. It's a bit subtle, but definitely critical. Group replication just won't start if you've upgraded your MySQL server using the upgrade minimal option.
Upgrade minimal. Why that specific one?
Because that minimal option, well, it doesn't update all the internal system tables. And group replication relies on some of those specific tables being fully up to date to work correctly. So the server might seem upgraded, but internally, GR finds things aren't compatible, and nope, it won't start. A small detail, but a big potential problem during maintenance.
Good heads up there. Okay, let's get into locks. This sounds interesting. Gap locks. My understanding is they lock the space between records to stop phantom reads, right? But then GR certification doesn't account for them. That sounds problematic. Why ignore them?
It is fascinating, and it's where distributed systems meet storage engine internals. So a gap lock, like you said, locks that empty space between index records, stops others inserting there, prevents phantoms. But GR's certification process, how it decides if transactions are safe to commit everywhere, it just doesn't see these InnoDB gap locks.
It doesn't see them.
Nope. Because that lock information is purely internal to InnoDB. It's not exposed externally in a way that the group replication layer can use for its distributed conflict checks. So while things might look safe locally on one server because of a gap lock, GR itself is blind to it. Conflicts could potentially slip through in the group because it doesn't factor that lock in.
Wow. So local safety doesn't mean global safety if you rely only on gap locks. That's a big one. Does this blindness extend to other locks, like explicit lock tables or those get lock named locks?
Exactly the same issue. This certification process also completely ignores LOC table statements and named locks acquired with getLock. Like the gap locks, they just aren't part of GR's distributed conflict detection math. The group validates transactions based on data changes, rows affected, but it doesn't check if someone holds an explicit table lock or a named lock somewhere.
Okay, so that means potential inconsistencies if applications aren't designed carefully around this.
Precisely. A local lock might stop a conflict on server A, but server B might proceed with a conflicting transaction because the group certification didn't see server A's lock, leads to data divergence. You have to be aware GR focuses on row-level write conflicts primarily.
That's a huge clarification. Okay, shifting slightly to data integrity. Binary log checksums. These seem pretty standard for verifying data, but there's a nuance with GR.
There is, yeah, a crucial distinction. GR does support bin log checksums, like bin log checksum CRC32, for general replication integrity. That's fine. However, those checksums are specifically not used to verify the incoming events on the group replication applier channel.
The applier channel. That's the main one GR uses internally.
Exactly. That's the channel members use to get and apply transactions from other members within the group. No checksum verification happens there.
Huh. Okay, so if not there, where are checksums used within the GR world?
They are used on other standard MySQL replication channels you might have running alongside GR. And they're also used during distributed recovery. You know, when a new member joins and needs to clone data or an existing member is catching up, checksums are used then. But for the core moment-to-moment replication between active members, the system relies on the group communication protocol's inherent consistency guarantees, not per-event checksums on that applier channel.
Okay, got it. Specific pathway, no checksums there. That kind of leads into consistency levels, specifically serializable. That's the strictest level, guarantees perfect order. How does that fare in group replication?
Well, serializable is indeed the strictest, making transactions seem like they run one by one, no conflicts. But in multi-primary GR setups, it's simply not supported by default. If you try to run a transaction set to serializable, GR will just refuse it.
Refuse it outright.
Yeah, it's really a design choice. Enforcing true serializability across multiple servers that can all accept writes. It's incredibly complex. It introduces a huge potential for distributed deadlocks and would likely kill performance in a highly concurrent environment like multi-primary GR. So it's a trade-off. You get the benefits of multi-primary writes, but you lose that absolute strictest isolation level.
Performance versus absolute strictness, a classic trade-off. Okay, building on that multi-primary complexity, what about doing schema changes, DDL, and data changes, DML, at the same time? Concurrent DDL and DML in multi-primary mode sounds risky.
It absolutely can be.
Yeah.
So DDL is things like create table, alter table, DML's insert, update, delete. The big challenge in multi-primary GR is when you have concurrent DDL and DML on the same object, like the same table, but initiated from different servers. That's not fully supported.
Not fully supported. What does that mean in practice?
It means there's a significant risk of undetected conflicts. Imagine server A is altering a table structure while server B is inserting data into that exact same table. Because both servers can accept writes, the distributed certification might not catch the subtle interactions between the structural change and the data change happening simultaneously. This can easily lead to data inconsistencies across the group. You need very careful application logic or procedures to handle schema changes in multi-primary.
Yikes. Sounds like something to avoid, if possible, or manage very carefully. What about database relationships, specifically those cascading foreign keys like on-delete cascade? They're convenient, but do they work well in multi-primary?
That's another tricky area for multi-primary. Multi-primary groups generally don't support tables with multi-level foreign key dependencies, especially if they use cascading constraints like on-delete cascade.
Why not? What's the conflict there?
The problem is that cascading actions, one delete, triggering potentially many other deletes or updates across related tables, can happen in slightly different orders or timings on different members in a multi-primary setup. If server A processes a delete and its cascades slightly differently or faster than server B, their data can diverge. The complexity of ensuring consistent cascading outcomes across distributed nodes is just too high. It fundamentally clashes with the distributed write model.
Okay, so convenience features in single server might become liabilities in distributed multi-primary. Got it. What about a common locking pattern like select for update? We use that all the time to stop race conditions. Does that cause trouble too?
Yes, even select spike date can lead to deadlocks, specifically in multi-primary mode.
Deadlocks.
The core reason is that the lock taken by select A for update is local to the server where the transaction started. It's not shared or seen by the other members in the group. So, server A might lock a row with select A for update. Server B, completely unaware of server A's local lock, might try to lock the same row. Boom, distributed deadlock. The system lacks that global lock visibility needed to prevent it.
Ah, the local versus global scope again. That seems to be a recurring theme. Let's talk filtering. How does GR handle replication filters? Can we filter what gets replicated within the group?
Well, you have to be careful. Global replication filters the ones that apply to all replication channels on a server. You absolutely cannot use those on GR members.
Why not?
Because if different members filtered out different data, the group would immediately become inconsistent. It breaks the whole point of GR maintaining identical data everywhere. However, you can use channel-specific filters, but only on replication channels that are not managed by group replication itself. So if you have a separate replication stream going off to an analytics box, you can filter that, but not the core GR channels.
Right. Protect the core consistency. Makes sense. Okay, bringing new members online. Cloning. GR handles cloning for recovery, but what about manual cloning by a DBA on a running cluster? Any restrictions?
Yes, there are. While GR's automatic cloning for recovery is fine, if a DBA wants to manually clone data onto a running group member, it's only allowed under specific conditions. The main rule is the manual clone operation must not remove and replace the recipient server's existing data directory.
How do you ensure that?
Typically, you need to use the data directory clause in your cloning command. This tells MySQL where to put the cloned data without wiping out the current member's data. It's basically a safety measure against accidentally destroying data on a live member during manual ops.
Got it. A safety net. What about the sheer size of the group? How many servers can you actually put in one GR group? Is there a limit?
There is, yes, a very clear maximum, 9. A single group replication group can have a maximum of 9 MySQL server members.
9. That seems specific.
It is. If you try to add a 10th member, the system will refuse it. The reason is all about performance and the stability of the group communication protocol, Paxos XCOM. Keeping it to 9 members or fewer helps ensure reliable performance and stable communication, especially on standard local networks. Going beyond that tends to introduce latency and instability that can compromise the high availability promise. It's a practical limit for the consensus mechanism.
Okay, 9 members max. Good, concrete number to remember for scaling plans. Finally, let's talk transaction size. The how big is too big question. Are there limits, and what happens if you hit them?
Oh yes, this is super important for operations. Very large transactions can cause real headaches in GR. For one, if the message carrying the transaction data takes too long to get copied across the group, the default timeout is only 5 seconds. Members might suspect the slow sender has failed and actually expel it from the group.
Expel it just for being slow with a big transaction. Ouch.
Yeah. And besides that risk, huge transactions just consume a ton of memory on all the members as they try to process and hold on to this massive change set. It can lead to performance dips or even out-of-memory errors. Double trouble.
So if you have a big job, like a bulk import, what can you do? Are there ways around it?
Definitely. First, there's a parameter. Group replication member expel timeout. You can increase this from the default 5 seconds to give larger transactions more time to propagate without triggering an unfair expulsion. But honestly, the best practice is usually to just limit transaction sizes proactively. If you have a massive load data, break it into smaller batches. It avoids the timeout risk and the memory pressure, making the whole system much more stable and predictable. And there are other settings too. Group replication transaction size limit defaults to about 143 MB. Bigger transactions get rolled back. Then there's group replication compression threshold. By default, messages over 1 MB get compressed. And even after compression, if they're still over group replication communication max message size default 10 MB, they get fragmented into smaller pieces for sending.
So lots of built-in handling. But are there absolute hard limits, like a point where even compression and fragmentation won't help?
Yes, there are underlying limits. The applier thread itself has a replica maximum packet limit, which defaults to 1 GB. That's one ceiling. And then the communication engine, XCOM, has its own absolute internal limit for a single message, which is around 4 GB. If your transaction, even after potential chunking, generates a component larger than that, it's just not going to work. That's the ultimate hard stop.
Wow, okay, that's a really thorough breakdown of the boundaries. So, summing up, we've gone from GTID quirks, lock blindness, isolation level issues, all the way to group size and transaction limits. Each one is a real design point to consider for using GR effectively, right? It's not about not using it, but using it smartly.
Exactly that. They aren't necessarily deal breakers, but they're crucial factors. They shape how you configure GR, how your application interacts with it, especially under high load or with specific needs. Understanding them means you can design around them, prevent weird behaviors, and actually achieve that robust consistency GR aims for, instead of just, crossing your fingers.
Fantastic. That was an incredibly useful deep dive. Hopefully everyone listening now has a much clearer picture of group replication's limitations. It really does turn potential problems into informed choices. Knowledge is power here.
It really is. And maybe that leaves you, the listener, with something to think about. If you were designing, say, a global e-commerce site, needing rock-solid consistency everywhere, or maybe a core banking system where data divergence is unthinkable, how would these specific limitations we discussed today influence your architecture using MySQL Group Replication? What trade-offs would you consciously make? What alternative patterns might you need? Something to mull over.
Great final thought. Definitely food for thought for anyone working with distributed databases. So if you found this deep dive valuable, please do like this podcast, share it with colleagues, friends, anyone who might find these database and HA insights useful. And of course, don't forget to subscribe to the channel for more deep dives like this one. Thanks so much for joining us, and we'll catch you on the next one.